Good morning everyone. This video contains tutorial talk to be presented at DASFAA Conference 2022. The topic of tutorial is time series anomaly detection tools, techniques and tricks. The presenters are from IBM. Myself Dhaval Patel and I am coordinating this tutorial. Other two presenters are Zoom and Marcus Muller. We first define the scope of the tutorial. We have carefully selected content of this tutorial to cover a wide variety of topics in a time series anomaly detection problem. At the end of the tutorial, attendee will be in a position to answer some of the key questions. What is time series and its various types? What is anomaly detection in a time series data? What is graphical Gaussian model and how to use them to solve the anomaly detection problem? How we design and develop the data science toolkit for anomaly detection? And the application of anomaly detection in the IoT domain. The tutorial also covers the API design for a web-based anomaly detection system. Interested AI developer will be able to utilize the API for their own dataset. At present, the API is hosted on IBM API Hub, and it is termed as an anomaly detection services for a time series data. Our tutorial is organized in a 4 topics. First, we start with the time series data, a brief introduction. Then my colleague Zoom will cover the anomaly detection problem for a time series data. In topic 3, I'm going to cover the data science toolkit named Anomaly Kits, as well as I will give a brief introduction about API Hub and anomaly detection learning path. In topic 4, Marcus is going to cover the application of anomaly detection in AI application, especially IoT related anomaly detection application. In topic 1, we give a brief introduction about time series data. Data come from everywhere. Data is being collected from grocery markets, e-commerce, stock exchange, hospitals, weather stations, and social media. And many of these different industrial segments, we have seen that the data are mostly a time series modality. So a time series is a sequence of data points that are measured typically at successive time and often spaced at a uniform time interval. In practice, we have seen 3 popular class of time series data, and they are like univariate time series, multivariate time series, and multi-time series, where we are collecting time series, let's say, for a different asset, right? So it's an asset-centric multi-time series. In the example, we have plotted a multivariate time series where we have captured the observation for a 3 sensor variable, sensor 1, sensor 2, and sensor 3, over a period of time. To give you a more why time series data analysis is important. So to give you more motivation, the time series data has a slightly different property than the IIT data. So this particular slide show you an example of a 10 univariate time series, which are coming from a different, a different instrument. So for example, the CPU, right? Like, so this is coming from a cloud machine, right? And we have also captured this stock market. This is the temperature time series. And you can see different time series has a different characteristics. And this is why the time series analysis become an interesting problem. You can also see that network traffic data and even the disease data, metrics code can also be treated as a time series data. So seeing the popularity of a time series data in a domain, we have seen that there is a huge amount of work has been done in academic work. And many of the research work that has been focused so far were primarily in 5 different areas, like clustering, classification, forecasting, regression, and anomaly detection. So you can categorize the different types of anomaly analytical tasks in a broadly two categories, supervised and unsupervised. Clustering and anomaly detection mostly fall in an unsupervised use case, and they are kind of considered like a more difficult problems than the supervised problem.
Now let me present some abnormal detection algorithm for time series data. Here we particularly interested in graphical model for abnormal detection. The reason is that we want the model that can handle the noisy data and can have the interpretability. So for that, we can explain our action in the downstream step. First, let's classify the type algorithms. So the type algorithm depend on the label availability. The first class of algorithms is the supervised learning algorithm. For that, the label available for both normal data and anomalies is similar to the regular classification, where we try to identify the to solve the imbalance classification problem. The second class method is the semi-supervised learning method. So for that, label available only for normal data. Most of current methods belong to this class. The last one is the unsupervised abnormal detection. No label are available. Our assumption is that abnormalities are very rare compared to normal data. So the way to build a machine learning model here, it really depends on the label data. For example, for this supervised learning method, we use the label from both the normal and abnormal data. And then we can validate the performance from the test data. But for the semi-supervised, we only use the label from the training data. And then we build the prediction model on the training data with the label. And for the last one is unsupervised. So the unsupervised algorithm most likely try to characterize the feature input, try to see how the feature input for given data is far from the population. Here we present a conceptual solution for abnormality detection algorithm. For this approach, there are three main steps. The first one is to learn a model from the normal behavior. So it can be supervised or unsupervised method. In this one, we particularly interested in the method to learn the distribution estimation from the observed data. In this step, we need to decide what type of parametric model to use, and then how to estimate the model parameter for the model. And this step is a very problem specific. So it depends on the application and depends on the data, and it might like the quite manual step. For that, we decide the type of model we're going to use. In the second step, we construct the abnormality score. This one depends on the type of model we build from the first step. For example, can be from the log likelihood, or can be come from the KL divergence or many other abnormal score method can be used, but it depends on the step number 1. The purpose for this step, we build a function that try to give the scalar or given data that quantify the degree of abnormalness. The purpose here try to capture the deviation of the object data from the normal data. And also one thing we need to keep in mind is how we can obtain the actionable information from this step. In the last step, we need to determine a threshold for abnormal score. For that, we can classify a sample whether it's a normal or abnormalness. In this step, it based on the performance matrix, like the true positive and true negative accuracy. And given the threshold, we can reflect, for example, if score exceeds the threshold. Step 2 and 3 in the many standard method exist. So it doesn't require much about the manual work. So mostly research focus on step number 1. Here's one example. We can use the multiple variate Gaussian for outlier detection. So given the data, we apply the step number 1 to learn the multivariate Gaussian. It is the graphical model. The graph here for the S that give the dependency between variables. If there is no S, we can claim that the variable are independent, condition independent. And then we use the log likelihood to compute the abnormal score. This one compute for the test data. And this one is from the step number 1, and this one step number 2. And we can, from step number 2, we can decide the threshold. For that, we can use to classify the sample, either normal data or abnormalities. In this talk, we introduce the different techniques to learn the density function beyond the graphical model. For that, we need to learn the distribution to determine abnormalities. So we introduced 3 different techniques. In the first application, where a single mode model is good enough. So for that, we introduced the DASFAA Gaussian mixture model to learn the distribution. In some application, there are some multimodality nature. For that, we use the several mode model. In this case, we use the mixture of Gaussian. And we introduce the new notation about the mixture gauge for the model. And the last one is about the in the cohort notation. For that, we have multiple assets, and they share many similarity, and how we can customize and to build individual model for each asset by leverage the common data between all the population. For that, we call the multi-model, multi-asset learning. Now, let me start with the review the Gaussian graphical model. Given the multivariate data, we use the GGM to learn the multivariate Gaussian distribution. And the good thing about the graphical model, In that, we can explain the behavior in the system. For example, here, if there is a connection, we can see that there is correlation between two variables. In other case, there is no edges between two nodes, so we can know that they are conditional dependent. For that, it can have the downstream task, try to, when we make the decision, when we do the maintenance or not. In the literature, it is very common to use a convex approach. Here, we saw a convex optimization problem. The first one is the likelihood, and the second term is about the regularization that impose the sparsity condition on the graphical model. Without this sparsity condition, we can see that the matrix is very dense. That's because of the noise on the data, and it might downgrade the performance of the prediction model. For that reason, we typically impose the sparsity condition. But we introduce a new technique to impose the sparsity. For that, we try to leverage exact regulation. For that, we use the L0 term. L0 here is that the try to impose the maximal allowed number of non-zero. That's the meaning of L0, that the count the number of non-zero in the matrix, and we directly impose the condition. But we also impose the robustness condition on the entry of the matrix. For that, we include the L2 norm here. In the next slide, we can show the benefit by using our elastic L0 model. For that, we combine L0 with the L2. We can see that for the L1 model, in terms of the accuracy, here we measure the true negative rate and true positive rate. And we can see that for the L1, it can have the low value for the true positive rate. And by applying the L0 model, we can increase the performance. And that we can have the better prediction on the graph structure of the graphical model. And we see that in terms of like solving time, even our problems that look like they're more complicated, but we can solve it efficiently. Now let's see how we apply our graphical model in abnormal detection. Here we use the time window-based approach, meaning that we take a sample of the some sample beyond the time window, and then we build the graphical model that give us the dependency graph that comes from the training data. In the testing phase, we also learn the dependency graph. That's the graph from the testing phase. And then we compare the two graphs. That's the way we compute the abnormality score. That's the second step in the framework I presented before. And here, for the training data, we use the elastic model with the L0 norm to learn the dependency graph. Here we get this graph. In the testing phase, we slightly modify the model. For that, we transfer some graph structure from the training data to the testing phase, because we assume that the graph structure, there are some changes, but not significant. So for that, we include the transfer learning technique to the testing phase. And then we also impose a sparsity condition for the graphical model. And then we use information theoretical fraction in compute the abnormality score. In this one, we can compute the abnormality score for each variable by using the KL diversion. Now, let's move on to the second technique to learn the density function. In this scenario, we assume that the model have the multimodality nature. For that, we propose to use the Gaussian mixture model to learn the prediction function. In order to handle the noisy and the data, we leverage the sparsity technique. In this case, here our mixture model, that the convex combination of several components. Pi here the mixture weight, and mu is the mean, and sigma here the covariance. And here we impose the sparsity on the mixture weight. The meaning here, we try to take the least number of components that still represent the data. That we call sparsity on the mixture weight. And we also include the sparsity on the invert covariance matrix. That we call the double sparsity in our model. So by doing so, we can remove the irrelevant component from the model. So let's recap what our novel technique here. So we take the SPA graphical model at the basic building block. So we learn the set of the graphical model, and then we decide what the mixture weight for each component. And we impose both sparsity on the mixture weight and the graphical model. What's the problem with the current approach? If we go back to see what the current formulation to update the mixture weight, so that they give rise the following problem. We maximize this term with the constraint. If we want to have a sparsity, we can add some regularization. But we can see that this term, because of the log term, then pi can be never zero. So we can see that if we think the sparsity in the conventional sense, we never get a sparse solution because of this term. So for that reason, we introduce a new notation we call the epsilon sparsity solution. The meaning of this new definition is that we wish to find a vector that have a few significant large values, but many of them are very small. We cannot impose them equal zero. We only ask many of them either very small. For that, we use epsilon here. We require that many xi in absolute value is the less than epsilon. So we call the epsilon sparsity. When we have this definition, we can incorporate in the model to get the epsilon sparse solution for the mixture weight. For that, we introduce the mixed interprogramming for the mixture weight update. And here the formulation. And again, the meaning of this formulation, we wish to find a few components. That's the second term here. Is that count how many significant components in our model. And I want to minimize that. That's the meaning. And fortunately, we can have the quadratic time algorithm to solve for this model. So our approach is scalable because we can compute the sparse mixture weight in the fast manner. Let me show some experiment to show the benefit to apply the sparsity on the mixture weight. Here, our mixture model that have three components, and here the ground truth. If we use the L1 approach to learn, and we can get the sparse graphical model, we can see that they're sparse, and we also get the very few number of components. But when we zoom in, we see that some mixture weight here, the value is small. For example, here, pi 2 and pi 4, the value is small. And they are not shown in the ground truth. That's the drawback of the convex approach. By using our approach for the sparsity on the mixture weight, we can remove this one because we impose the condition that we utilize the mixture weight should have the large enough considered in our model, and also minimize the number of components in our model that we directly impose in our learning method. So for that, we're able to recover the ground truth. Now, let me move in another, the third method to learn the model for abnormal detection. In this case, we consider multitask, multi-model model for collective abnormal detection. So we know that production equipment is typically managed at a cohort. For example, in semiconductor, we have many tools. They operate quite in similar conditions. And also like the wind turbines, also we can see that they can operate at a cohort, and they can share many common in the data. And now the goal here, we try to build an individual model for each asset, but try to leverage the common data between them. So for this scenario, we need to handle the multi-assets and multi-model for the learning approach. So the straight solution here can have some serious limitation. So if we treat the system separately and create each model individually, one of the big issue here is the fault example may be too low for each asset. In another approach, if we build one universal model by disregarding individually, so for that, it might not applicable in some application because here the individuality will be ignored. So for that reason, we would like to build the prediction function for each asset and try to use the fault example from each asset. So what are our solutions here? Our solution here is again, we use the graphical model as the building block, and then build a common meta model across all the assets, and apply the learning to individual assets. The history data is used to build a common dictionary. The dictionary is the minimal number of submodels that can be used to learn predictive model of all assets. So we can think about here is a common model parameter. Is that the graphical models? And this one is the is the weight for each asset, is the asset specific. So we can learn a model for each asset by take the combination from the common model parameter. So what is the benefit over here? The benefit over here, our model by using the sparsity can better to handle the noise in the data. And furthermore, it can be highly interpretable. And our model is able to capture multimodality, which are the multi-operational state for an asset. So here an example when we compare with the state of the art. If we only use the mixture model, and then we only build a single model for all the assets. In other multitask learning, they can build a single model for each asset, but it only considers the single mode. In our case, we can build the multi-mode model for each asset. So for that, we call the multi-asset, multi-model model. Now, let's see how we can apply our methods in abnormality detection framework. Here we have the N assets, and our common dictionary is a sparsity graph. And for each asset, it can take different weight vectors from the dictionary. And then we obtain the model for each asset. Each asset note that the different because of the sparsity mixture weight. But we take all the data from all the assets to learn this parameter, to learn the graphical model, and to learn the sparse weight. From that, we can get the model for each asset. And then we can use this one to do the modeling. Then we can apply the second step to compute abnormality score. That in this case, without use log likelihood. So if there's some point over here, it gets the lower abnormality score. So no, this one is the low likelihood. But in terms of abnormality score, it's a high abnormality score. And then we can classify this one as the outlier. And at some point here, it can get the low abnormality score. So we can see that the Poisson normal. When we compare our method with the baseline method, as I said, because we can customize the individual model for each asset, so and also can handle the multimodality, and for that reason, it can have a good performance when we compare the baseline method. So I just show the third method to learn an abnormality algorithm. Here we handle the multi-asset. Thank you for your attention.
In topic 3, we discussed Toolkit for Data Scientists and API Hub. This slide shows you a framework that we have adopted to build the anomaly detection toolkit. One of the design principles that we have adopted is to be compatible with scikit-learn. A scikit-learn is a popular machine learning library to build a good supervised models, like to build a lot of classification models or regression models, they lack the support for a time series data, and that is what this particular toolkit. In topic 3, we cover toolkit for data scientists. In this slide, we have given a framework which we have adopted to build anomaly detection toolkit. The framework is SQL compliant in the sense on a scikit-learn library, which is very popular among machine learning and data scientists, as well as the developers. And we have used the scikit-learn library idea to kind of standardize the architecture. So the toolkit is divided in a 4-layer. The bottommost layer is the anomaly operator. The anomaly operators can be transformer, can be estimators, can be detector, can be stationarizer. So the bottom layer is made up of the individual component. Say, for example, Zoom discussed the Gaussian graphical model as an anomaly detection estimator. So it will come as an estimator. In many times, when you get a time series data, you want to post-process them. Say, for example, you want to remove the trend of your time series data. Those components can fall into the stationarizer. So we have come up with a design of different types of component, which we call as an anomaly operator. Once you have an anomaly operators developed, a lot of times we glue them together. Say, for example, given a time series data, I want to first standardize the data, like do the min-max operation, and then I want to send it to the Gaussian graphical model. So this is an example of a pipeline. What we observed in the case of the anomaly detection, that pipeline composition is a slightly different. And what we have done is that we have standardized a 4-way of building anomaly detection pipeline. These 4 pipelines are, we have given a name like a deep AD, window AD, relationship AD, and a reconstruction AD. Let me give you an example of the reconstruction AD. So a lot of time data scientists build a machine learning pipeline, which is based on an autoencoder architecture. And where given a time series data, you use autoencoder architecture to reconstruct the data. And then you try to identify the differences between the original data and the reconstruction data and discover the anomaly. So if a data scientist is trying to build a pipeline based on this idea, a data scientist can use a reconstruction AD. In another example, like the Zoom presented Gaussian graphical model actually falls in the relationship AD type of a machine learning, a type of an anomaly detector. So in case of the relationship AD, what we do is that if you have a multivariate time series data and you are interested to discover the normal relationship between pair of variable or maybe multiple variables, and then you expect that when the anomaly happens, maybe the relationship between some pair of variable may be broken, and then you declare an anomaly happen, right? So sometimes data scientists want to build anomaly detection model by looking into the relationship between the variable, and then they build the anomaly model. If that is the case, then the relationship AD will help you to kind of build a model. Sometimes we have seen cases where anomaly detection models are based on a time series forecasting idea, where you forecast the value, and when the ground truth is available, you calculate the difference between the forecasted value and the ground truth, and then you obtain the error between these two forecasted and the ground truth over a period of time, and then you decide whether the anomaly has happened or not. all those kind of an idea are standardized with using DPD, which is basically deep ensemble based time series forecasting, and then use it. So what we have done as a part of this anomaly kits toolkit is standardization of discovering anomaly problem, right? Like standardizing how we solve the anomaly detection problem with using a pipeline concept, right? And the pipeline is composed of the unit which are coming from the bottom of there. Now, once somebody give you the data, and your interest is you always try to kind of a best anomaly model, because that's always an interest, right? So the data scientists normally want to evaluate more than one anomaly pipeline, and then they want to pick up the one which is the best. In summary, we have seen cases where a data scientist or engineer run more than 100 pipelines on a given data set and try to identify the rank. Now, how do we specify 100 pipelines? And that is what the anomaly workflow helps a data scientist on specifying how to define a search space for a given anomaly problem. So we have a concept of directed acyclic graph, and I can refer your paper in the reference section, which gives a detail about how a data scientist is formulating a directed acyclic graph, which help them to specify more than 100 pipelines. Now, not only the pipeline, but sometimes you also want to specify the parameter for each pipeline. And that is what the parameter tuning module actually take care for the anomaly workflow. So this is a third layer on the left side. Assume data scientists use this workflow and created a 1000 pipeline. We have seen how do we run this 1000 pipeline in a scalable manner. You need a supported execution engine, right? So that is what being covered in a third layer, right side, execution engine. So the purpose of an execution engine is to give you a capability to give which you can use to scale the exploration problem, right? Like how you can scale, how you can explore like a 1000, 10,000 or millions pipeline and find out the best. And see, and based on the discussion I described that, some of the pipelines will be CPU intensive, some of the pipeline will be GPU intensive. The execution engine should able to give you all the need, right? Like say, okay, we wanted to use GPUs, we want to use a Spark, or we want to use a serverless computing, right? So we have come up with a solution which is able to meet all these things. So now we are able to specify the anomaly workflow. We are able to specify the execution engine. We also build a lot of applications, right? Like saying is that the use cases, right? So now use cases can be novelty detection, use cases can be unsupervised anomaly detection, use cases can be outliers. So all the applications actually sit on the top layer, where we can specify the anomaly use cases. And the detail of this particular slide, you can read our AAAI 2022 papers. So this framework, what does it take as an input? So the input can be univariate time series, or it can be multivariate time series. In summary, it actually takes NumPy array or Panda data frame as supported by scikit-learn. Now I'm going to the lower layer of our anomaly detection framework, estimators. So let me give you a kind of an estimator that we have developed as a part of our toolkit. So far, we have a wide range of estimator available in our toolkit. And these estimators are categorized in a statistical, machine learning, or deep learning base. some of the statistical anomaly operators, Q sums, or even hoteling T-square are very useful in many industrial applications. Jung covered Gaussian graphical model in detail, but apart from Gaussian graphical model, we do have a couple of many other anomaly detection algorithms implemented by reading a lot of literature work. And some of the algorithms are also available in scikit-learn, like isolation forest, one class SVM. What we have done as a part of our toolkit is standardize the definition of each of these operator. So each and every operator, which is a kind of an estimator, comes with fit, predict, anomaly score, and decision function. So each and every class, each and every algorithm actually implement these 4 public methods. So let me give you a data science view of our toolkit. So on the left side, on the bottom, this side, this is one time series data that I have plotted in one of our earlier slide. So if you look at this data, and let's define that we are interested in identifying the anomaly detection for a given time series. So this time series is given, and we have been asked, can we identify a place where the anomaly happens? So let's say I'm a data scientist and I want to identify the anomaly in the time series data. I also know the scikit-learn library, and one of the algorithm which is very popular in scikit-learn library is isolation forest. So as a data scientist, I will say, okay, let me make a very simple try. I load the data. So I have given a code snippet. So I load the data. I also imported the isolation forest classifier, anomaly detector. So I initialized the class with the default parameters. And I know it's a univariate data, but let me feed the univariate data. So I feed the data. And then I use a decisions function to actually obtain the anomaly score. And I plotted the anomaly score as follows. In this particular plot, the lower score means the more anomaly, because it's an isolation forest. So lower the score, you can say the anomaly. And what you see is that we are saying is that the anomaly is at the start and the anomaly is toward the end. Okay. Now we were expecting that the anomaly score should be high around this place, but it doesn't happen. Why? So let me answer that question. This is a time series data, and we were using a non-time series data algorithms on a time series data. Now, time series data has structures, seasonalities, periodicities, and then a lot of stochastic process, noise. So, in order to address this, and time series data is not IID, so the simplest solution that we have seen the data scientists adopt is, given a time series data, you slide a window of certain length and then translate the time series data into some sort of tabular data. So let me introduce a window AD pipeline. So suppose the data scientist is interested on building the anomaly model using this principle, saying is that given a time series data, I would like to slide a window at a regular interval. And then I want to use an open source anomaly detector like an isolation forest. So the window AD pipeline that we have built into our toolkit may able to help data scientists to write this pipeline. So you can see the code snippet that we load the data, we build the window AD pipeline. While building the window AD pipeline, I'm saying I want to flatten my time series data. So I will do this flattening. And then I want to actually apply isolation forest in a flattened data. Right? When you do the flattening, you should use the window length is equal to 5. And this other column, target column and feature columns are in a placeholder saying is that where in your data, where is the target and feature column. For a time being, I skip the scoring method detail, but this is how a very simply in a couple of line, you can create a window AD pipeline and then say, okay, fit, right? And once you do the fit, you call the predict in order to get the anomaly score on the training data, right? So I think you can see how the architecture of pipeline looks like, okay? In these slides, I run the window AD pipeline on the data set and I obtain the anomaly score. Now, interestingly, my anomaly score is still, yeah. So the anomaly score is not as I was expecting. Why? One of the observation, maybe the lookback window that I set is not an appropriate. So data scientists may like to try certain parameter. Let me change the lookback. Okay. So we now from 5, we make it 15. And we run the same pipeline. And we say that, do I see any effect? Yes, we do see the effect in the score, but we don't see that the anomaly score was as expected. We were. Now, this is very much, even if you do min-max scaling, how you may have similar results. So the current pipeline actually lacks any operation which post-process the data, right? So let us do that, right? We added one extra operator which actually post-process your time series data. In this case, the operator that we choose was data stationarizer. We think that it's a time series data and it may have some kind of trend. And if you detect the trend, you automatically remove the trend and then retrain the data. And that's what the data stationarizers component do. So as a data scientist, he just added an extra component saying is that let me add the data stationarizer component in the start. Now my component is data stationarizer followed by flatten followed by cap. We do have a lookback window and all the other remaining parameters remain same. And what you see here is the anomaly score as expected location went up. So this was a very simple example how a data scientist can build a good pipeline, right? I would say like a pipeline which composed of 3 components. One is data. I mean, this one is a data stationarizer. Then this is data transformer, and then this is the the open source anomaly detection algorithm, so outlier detection algorithm. Right? You may think that I want to change the lookback window. Maybe the magic happens because we set the lookback window to 5. So you can try lookback window is equal to 15. Yes, there is definitely some effect on the value of a lookback and to the score, right? But we still see that the anomaly score is high around the expected location, around 2025. Okay. So anomaly toolkit that we have designed, we know that when a data scientist gets the data set, he may like to try different types of anomaly detection algorithm. So in the previous slide, I show you how we can build a window AD based anomaly detection, where given a time series data, you slide a predefined length of the window across the time series, turn the time series into the sort of tabular or IID data, and then build the model and use the existing outlier detector as an algorithm. But as I mentioned, the framework support multiple types of anomaly detection modeling, right? Like window AD, prediction AD, or reconstruction AD, right? So assume a data scientist like to switch from window AD to prediction based AD. How much modification he is expected to do? So the left side is what we have gone through is a window AD. And on the right side is an example of a thread AD. Now you can clearly see that the modifications are very minor. And yes, data scientists must be kind of careful while choosing the last layer, which is, in case of the window AD, it should be the outlier detection approach. In the right side, in case of the prediction-based anomaly detection, the last layer should be the regressor, which is linear regression, is the next example. The rest of the parameters still remain same. So the design that we have adopted is switching between different anomaly pipelines should be easy and more convenient. And by adopting this kind of a design, data scientist is capable to explore like different types of anomaly pipelines. Okay. So let me summarize it, right? That the toolkit that we have built, and we have also published it, actually provide a formalization and implementation of scikit-learn-based exemplar anomaly pipeline to cover a wide range of anomaly detection approach. This covers spread AD, deep AD, window AD, relationship AD, and reconstruction. Now, one thing I want to mention is whenever you apply any anomaly detection pipeline, at the end of the day, anomaly detection pipeline generate a real value score, which we say is an anomaly score. And in a large, most of the time, we have seen that the data scientist or even the end user has come back on asking, how do I interpret this real valued anomaly score? So to answer that question, we have seen the literature has adopted a concept of thresholding an anomaly. So each and every anomaly algorithm is supposed to also provide an anomaly threshold. And this threshold an end user can use, saying is that if my anomaly score is higher than this anomaly threshold, then I will consider it's an anomaly. Otherwise, I will consider it's just a noise. Now, because this is a time series data, you may end up having two types of anomaly thresholding. One is dynamic, another is a static. Static anomaly thresholding is a constant value, right? Once you decide, it doesn't change. Versus dynamic anomaly thresholding actually change over a period of time, and it adapts to the error that you are encountering in your recent past. What we have done as a part of this toolkit is standardization of this dynamic and static anomaly thresholding techniques. So far, we have Q-scope, chi-square, sliding window threshold, adaptive sliding window threshold technique. So let me summarize. What I covered as a part of this topic 3 is a brief introduction about 4 types of anomaly detection pipeline. And once you have anomaly pipeline set up, they will emit on a real value anomaly score. And in order to make a good understanding of this anomaly score, we also support 2 different types of thresholding. One is a static thresholding and another one is a dynamic thresholding. Static thresholding doesn't change over time. And we have a couple of different types of uh, uh, thresholding technique, like contamination based, adaptive contamination, Q, robust Q score, And uh, and there is one more aspect is we have seen, because anomaly detection is mostly purely like an unsupervised use case where label of the data is not available at the start. But as you make a progress, let's say you deploy the anomaly model for a real use case, over a period of time, you may start collecting a tiny amount of a label. So we have seen that there are two popular use cases which are being supported by our toolkit. One is an unsupervised exploration, where you do not provide any label information upfront. And another one is a semi-supervised exploration, where you provide a small amount of labeling information that we do not make use of during the training, but we make use of selecting the right algorithm. In case of the unsupervised exploration, since there is no label is provided, the toolkit come up with a ranking mechanism. So a data scientist still can run multiple algorithms on a given data set and can obtain the rank on their data. Now I will discuss the Now I will discuss the deployment of anomaly detection toolkit on API Hub, which we are terming as an anomaly detection services, a web-based anomaly detection service. The service that we have deployed on API Hub supports univariate and multivariate time series. They support batch, train, and test. They support up to 100 active users. And it doesn't require any installations and infrastructures. How, as a user, I can access the anomaly detection services? So you need to go to the developer.ibm.com, and then you may search for anomaly detection on a time series as a keyword, and it will bring you to the API. Once you go to this web page, you need to subscribe to these services. So when you click Get Trial Subscription, it will bring you to another web page where you may enter your user ID and password, and you register for the services. And as a part of the registration, it will give you the credential. Credentials are for these services, and they are specifically client ID and client secrets. Once you have this client ID and client secret, you can use any of these univariate anomaly detection, multivariate anomaly detection by providing these two values as a part of your service call. In order to go in a depth, saying is that what are the steps a user need to do in order to run an anomaly detection algorithms on the API Hub, we have come up with an anomaly detection learning path. you can enroll into this learning path activity, which will walk through your series of a step, saying is that it will give you a brief introduction about anomaly detection. It will also help you, how do I start to use the API detection, API, and then it will bring you to the use case. So this anomaly detection learning path is useful for a new user who is willing to try a shot. Apart from these learning path, we have also make available several notebooks on this open source repository, and it is composed of multiple notebook. You are free to take any notebook in order to try. What modification you need to do is that you need to replace the notebook by using client ID and client secret that is provided to you. These two informations, if you adjust it, you will able to run the couple of notebooks that are available as a code pattern. So let me bring it back to our core API services, right? So once you finish your trial subscriptions and you have client ID and client secret, you are free to make a multiple API call. Some of the call is my connection has been established or not, which we recommend you to do at the first. Connection check only required client ID and client secret. Get result is like anomaly detection, making an anomaly detection request through the API. It is not a synchronous call. So it is an asynchronous call, right? So when you make any of these request, you will get a job ID, and that job ID you can use as a part of the get results. So get result is another API where you need client ID, client secret, as well as job ID to get the results of the submitted task. And these are the two common area, right, where you submit the request to do the anomaly detection, either on univariate data or on multivariate data. Now, as I discussed, that there are multiple different types of anomaly algorithms are already present, right? When you are about to submit a job, you might also like to provide your preference, right? Okay, so when you make a request to the anomaly API hub, your request actually went through a series of operations. Saying is that first we do your data inspection and validation. Then we see whether your time series data is uniformly sampled or not. If you remember, the loopback window in the window ID is one of the important parameters. We have a capability to automatically infer the loopback window as a part of the services, so user doesn't need to specify it. Then we create an anomaly pipeline based on the user preference. So user may say that he is interested in a building window AD pipeline and he want to use isolation forest. So we create an anomaly pipeline in this phase and then run the anomaly pipeline on the data that user provided. Once the anomaly pipeline is trained, we can generate the anomaly score and as well as thresholding, right? Once the threshold is available, we are in position to also generate the anomaly label. And then in some of the cases, as Jung mentioned, that some of the algorithms come with explanation capability, like which variable is more important when I say that the anomaly score is high. So those kind of additional information, either variable wise, is also available in a form of the severity or contribution. This is the end of a topic 3.
Oh, my name is Markus Müller, and I'm the data scientist for Maximized Monitor, a product in the industrial scenario area. Well, let's focus today on how we do anomaly detection in this scenario. It's, as I said, typically industry-specific IoT scenarios, could be SCADA data as well. And I would like to start with an example about developing a model for a specific customer case. The next step would be deploying and running a model in our data pipeline. Once we have developed a model, it needs to do some inference. And then finally, I would like to cover what Monitor offers out of the box, so-called catalog functions for anomaly detection. Let's start with the case of anomaly detection for pumps. Pumps, or pump manufacturers and operators, tend to be quite interested in vibration. Vibration is a crucial metric for failure prediction, impending failures, especially excessive vibration. And you see a typical pump that this particular pump manufacturer has in his program. You see the operating range and with regard to the flow rate and the head, and on the right you see typical data, root mean squares in the z-axis, an hourly trend, some critical thresholds that indicates in this particular example a couple of anomalies. And in this pump example, this instance had some issues with the seals and the ball bearings, slow degrading over time. That tends to occur gradually and can be introspected by looking at the vibration. It tends to be connected to age. That's an aging problem. And we have some other cases where vibration appear out of the blue quite suddenly, cavitation related mostly. And this is what the customer is interested in. Let's talk about pump vibration from a metric perspective. So what's interested is the displacement, the endpoints of the vibration motion, the velocity, how fast it happens, and the acceleration, and negative acceleration, of course. So we have 4 primary metrics: the frequency, how often it takes place, displacement, velocity, and acceleration, of course. And we have secondary metrics because measuring the primary metrics will lead to a lot of data. So we have to focus on the secondary metrics. That will be peak amplitude, actually close to displacement, and the root mean square, mostly a rough integral of the velocity over time. Well, looking at vibration can be done from various angles. So once you have that time series data of root mean square or peak, then you can consider that from the original time domain. You can look at the frequency domain. Mostly, or quite often, you see it at the joint domain employing short-term fast Fourier transforms. And you can look at the distribution, looking for peaks in the distribution, some modal analysis. And this gives rise to the various categories. So you can start looking at the overall level of vibration, the energy spent. That's quite easy, that's quick and dirty, that's relatively easy to consider and analyze. If you want to go more into the depth, you can start doing spectral analysis, frequency or joint domain, starting with looking at isolated frequencies of interest related to the impeller motion, shocks. You can up to looking at the low pitches, substring analysis, and amplify the low pitches, disregarding, or let's say, not disregarding, but not focusing on the rest. Let's look closer at spectral analysis. So the vibration spectrum, of course, reflects anything that might be wrong with the pump, starting with some mechanical issues like imbalance, some misalignment, looseness, just a screw came loose, but also resonance and natural frequencies, up to empty spaces and bubbles, cavitations that take place if you increase the flow rate. And on the right side, you see a typical example. That's a velocity spectrum that shows the running speed, that shows the harmonics of that running speed. And a separate peak is bearing defect frequency. That should not be there, of course. In our case, when we investigated that real-life customer vibration data, we found out there is not much raw metrics, not even a short-term average root mean square, but it was spread over seconds in all three axes, and a flow rate metric every 5 seconds along with the power. So that's not that much information. And due to the cube law, flow rate and power are cubically proportional. So power won't add much information. We just disregarded it. So we have to cope with, let's say, 2 metrics focusing on a single axis. And you see in this example, the vibration in yellow and the flow rate. It's mostly in 2 areas, so pump in low and 0 and high speed, the flow rate in blue over 2 months. Well, how to tackle that? So the first idea is, can we predict something from vibration from impeller speed or flow rates? That's not likely. Cavitations is a typical example for vibration that appear quite suddenly, because that's a chaotic system. While high flow rates increase the chance, it might happen or it might not. And furthermore, as I pointed out, sampling rates for vibration and flow rates are different. So you might not notice the effects in the right causality. So we agreed to focus on plane outliers. This vibration is excessively high because it doesn't happen very often, or let's say it happens rarely, instead of predicting something. So we thought, could we establish bounds on vibration with regard to the flow rate? Vibration should be higher if more water flows through a pump. And this is a yes. So with plain KDE, the kernel density estimates, we could find that the pumps exhibit individual profiles with areas of low density with regard to flow rate and the opposite. The example is on the left. But bivariate KDE is expensive to evaluate. So we looked for an alternative to that. And for some pumps, in this example, yes, it would work quite well. The Gaussian mixture model would work for them. And for others, it does not. So the alternative is to find a function pair with a mean and a variance depending on the flow rate to roughly approximate the real density. And we took to variational inference and inspired by a variational autoencoder architecture, and we just dropped the decoder for good. And the latent space is not really a latent space, it's actually an approximation of the real distribution of the data. That's at least the idea. And well, I can tell it worked out quite well. So this is the architecture. We have a quite simple approach for the mean. It's not really linear, but almost. And a bit more nonlinearity for the log variance. We started with 2 layers and found out 3 layers is just fine from experimenting. So we went with 3 layers. And we also attempted to reduce training time a bit, and especially to get more tighter bounds. So we took to importance weighted elbow loss functions. It's not that much effort, and it actually gave tighter results. And we also massaged the prior so that it's not too far off the mark. You do not need too much data to see convergence. So the prior and the mean is taken from the target to begin with. And this is the result. The pump profile actually in terms of flow velocity versus vibration. So we agreed to ignore vibration when the flow is 0. So the pump is not in motion. There should not be any vibration unless it's settling down. We have one single isolated low flow issue here. Something that's wrong, but it's just an isolated event when the flow was low. And we see cavitations at very high flow rate, which is quite reasonable. And now transferring that back or transforming that back to the original time series data, we see one isolated high vibration event that we simply ignore because the flow is 0 flow rate, and a couple of outliers where we believe that's cavitations, and one isolated event where we don't know the root cause, but it's excessively high. So up to the pros and cons. Essentially, pro for that model is you get much more granular detection of excessive vibration because you take the flow rate that should be an effect on vibration into account. And you can use the model drift as an early warning of an impending failure. So if you get to see ongoing vibration alarms, something's going wrong. It spells trouble. As a con, it takes some data, roughly 2 months of data to be useful. And of course, it requires model training and the infrastructure to do that. So the next step, what do we do with that model? If we opted for Pro, you would have to deploy it in a monitor framework, in the monitor infrastructure. And the next step will be just about that, how to deploy and run a model in our data pipeline, in monitor. And here you can see Maximo Asset Monitor's component, how they face the world, what to do with the data, and where it is exposed to the end user. So essentially, we take the data over various input paths. It could be an IoT device that sends data to MQTT. It could be a SCADA enterprise historian, where we extract the data and push it into the system, or something else. There's a platform service that links all the various elements together, especially saving data in a database, saving logs in Cloud Object Store, linking Kafka, that's event stream. And you could even tunnel through firewalls with the secure gateway, but that's not the interesting part. The interesting part is the analytics box, where you can read KPI functions. And a typical KPI function would be exactly that anomaly detector that we have seen before. And the results of that analytics is exposed to a dashboard, via dashboard, to the various types of consumers. In our case, it's mostly subject matter experts that actually know where to look at. And this is the data flow. So actually, the data is generated or measured with sensors It's sent, could be an IoT device or the various different paths, to the platform service. It's reflected in a data lake, the raw data. It's periodically extracted from the box number 4. That's analytics service functions. That's the data pipeline where the analytics, like the anomaly scoring, is taking place. The results of that are reflected back in the data lake and exposed to the process engineer via UI. And now I'm focusing closer on the monitor data pipeline. As I said, it's running periodically. I would like to focus now on the monitor data pipeline in more detail. Well, we start with extracting the raw data that came from the devices in the first step to assemble a pandas data frame with a multi-index, so the index for timestamp and the device ID. And then it's passed through a sequence of functions to enrich the data and finally store the enriched data in the derived metrics table, the additional data columns. And the transformations could be a normalization of the data. It could be used to reduce dimensions, or as with the model, to predict or score something. And all these additional columns end up then, as I said, in the derived metrics table. And raw metrics, derived metrics, and of course raw dimensions, derived dimensions, serve to feed the UI to expose what's going on to the process engineer, the SME. Now we focus on model scoring the pipeline with a focus where the model came from and passing the data through the various functions. If it reaches a machine learning function that requires training data on a trained model, the trained model is pulled from DB2. The blob is stored in DB2. It's instantiated and turned into an active Python object. It's unpickled. And then it's called, the predict method is called, whatever the predict method actually is hiding. So that's a facade in front. Typically, it adds one or more pandas data frame columns that are passed to the next function until they end up in the database table, in the derived metrics table. The supervised learning transformer, that's how coding models in Monitor, that comes with the capability to add columns to the pandas data frames with a particular format, and it can manage mostly load model blobs from DB2 and instantiate them. Our new function is subclassing that to encapsulate the variational autoencoder-like model. And you can see it from some of the attributes like the learning rate, that's for ADAM, and the epochs that are not used for inferencing, of course, but for training. And coming to training, training is a manual step right now. We don't have a fully fledged data pipeline for training. We just have it for inference. So for training, you need a script, or here in this case, a Jupyter notebook. And foremost, you have to open the model table where the inference pipeline pulls the model blob from. Then you have to instantiate the custom function, tell it That's the next one. Train if there's no model yet. Auto train, delete model. Just delete anything that's there. Ignore it, override it. Specify the device type, T shadow pump of generation 5. And until you finally instantiate a mini pipeline and run the function. And as part of running the function, you just take the data that's in the pandas data frame, df_i, and train it successively one by one for all the pump data that's available. That's the multi-index. It takes its time, but it results in models, in trained models that are pushed out to DB2. That's part of the flow. And here the results in the monitor dashboard. It's just a screenshot, real life data from some way past. That's last year, 2021. And just the credibility interval and the real life data. That's the result of the model. So the last step is to look deeper into the catalog function, what's built into monitor for anomaly detection. That's mostly unsupervised, untrainable models that just look at outliers from various different angles. So we look for anomaly patterns, but very specific ones. For example, a signal, a varying signal that suddenly out of the blue becomes a flat line, or a varying signal that is super steep out of the blue. Of course, thresholds, just a peak maximum or minimum. The opposite, a flat line that suddenly becomes a very agitated signal. Or if you have the case of no data, you have a sensor failure, or equipment goes offline out of the blue. So you receive temperature data every 5 seconds. And now you haven't seen something for a minute. That's an outlier. Or you have some target that depends on a set of features. And out of the blue, the actual and the predicted deviates beyond this predefined threshold. And of course, you can delegate anomaly detection to external AI models, something that you deployed or somebody deployed on WML. Now to the catalog function that we support. So we have the regular workhorse, that's the k-means anomaly score. Well, that tends to return a quite useful score in most examples. And this one, along with all the other scoring methods that are built in, it starts with imputing missing values by interpolation. It normalizes the data, and the normalization coefficients are learned the first run from the data at hand. Then we cut the time series data into overlapping snippets so that we get n-dimensional, typically 12-dimensional vectors. And then we run k-means clustering, sort the clusters into large, small. For the large cluster members, that's the distance to the center of the centroid. And for the small cluster members, that could be outliers by themselves, it's the distance to the center of the closest large cluster centroid. Spectral is the quick and dirty thing. That's useful if speed is king. So if you are scoring, for example, from lots of data points, that happens sometimes. We have a case where we have 10,000 data points or more. It starts as usual, imputation, normalization, cutting into snippets, and then we apply short-term fast Fourier transform, compute the spectral density, and then run just the z-score. No data anomaly score starts with transforming the gap length into time series data by itself. So if you have a large gap out of the blue and had small gaps before, that's an anomaly. And then we apply the typical spectral density thing. Matrix profile, again, all the various steps. The algorithm relies on finding siblings that are pretty close in the neighborhood. If you find something that's pretty close and similar to what you have seen before, that's not an anomaly. If the next similar data snippet is quite far away, that's likely to be an anomaly. And it applies to speed up computation. It applies short-term Fourier transform to find neighbors, to find something that's similar. It's reliable, but it's rarely used because it was shipped later than the rest. We have an anomaly scorer based on fast MCD. That's rarely used. It's relatively hard on the CPU. If you starting with FFT feature extraction in front, it's quite often used and quite useful. And we have one that's based on separate analysis, so it amplifies low pitches. That's quite rarely used, but it's used. And we have one tool to rule them all model. It's a model fit data science. That's a gradient booster regressor. That's a pipeline with a standard scaler in front, then trains a gradient booster on the fly with the data that it gets in the first run, saves the model blob, and does scoring from that. Actually, it works surprisingly well. So it's quite useful. So I would like to thank you for your time. It was a pleasure, and I'm open for questions now.